I can't speak for androids, but I can tell you that I've sure been dreaming a lot about robots recently. But lately I've found myself distracted by various other projects. But the whole time I have been dreaming about Marge. And more specifically, dreaming about Marge's elbow. And don't worry, this is completely normal for me at this point. So no more delays, it's time to buckle down and tackle the next stage in Marge's development, and that's the elbow. And as usual, there's a lot going on here. For one thing, it contains the two elbow joints, joints 3 and 4, as well as the motor for joint 4. The elbow's frame also has to be strong enough to support everything else we've built up to this point, namely the forearm and wrist. But the elbow is still halfway down the length of the arm, so it's still important that we keep the weight down as much as possible. In keeping with the general design of this robot, we're directly coupling all the joints to their respective gearboxes to maximize stiffness and reduce backlash. So to be honest, looking at all these parts is making me start to panic just a little bit. So I think it's best if we break things down piece by piece and take it one step at a time. Because if I start to think about all this too much, I'm just gonna lose my nerve. Up until now, I've just been working my way down the arm. And I don't see any reason to stop now. So I'm going to begin with all the components that make up the Axis 4 drive system. So the gearbox is once again a harmonic drive, and this gearbox has to go somewhere. So first step is the gearbox mounting plate. And this plate serves the dual purpose of reinforcing the frame, as well as keeping the gearbox aligned along the center line of the elbow. I could certainly tackle this part entirely in the CNC. An interpolated hole should be sufficient for the gearbox fit. However, I need a little practice on the lathe, so I'm going to try something a little different for this part. So I started with a slightly oversized piece of plate stock, and used a punch to mark the center of the plate. A dead center placed between the punch mark and the live center mounted in the tailstock provided an easy way to dial in the part. The part then gets center drilled and drilled out with my largest drill, which is only 1/2 inch unfortunately, so there's still a great deal of material that needs to go. Next I faced off the plate to create the front reference. And then it was just a ton of boring. The through bore is not particularly critical, I just had to be careful to avoid the chuck jaws as the bore got bigger. The critical feature is the shallow bore that locates the gearbox. And these shallow bores are actually pretty tough to measure, as the telescoping bore gauge can't get deep enough to measure 100% accurately. I could sort of test fit the part in situ, but the chuck jaws prevented the gearbox from seating fully. So I kinda had to take a guess as to when it was correct. And the fit ended up okay. As Blondie Hack says, I'd rather be lucky than good. And I've been struggling so much with boring on the lathe that I'm just happy if I can even get it close. And then it was time to fixture the plate in the CNC. And those who've joined me before will know that I'm a big fan of super glue and paper tape when it comes to fixturing parts. However, I will admit the paper tape has been a potential source of inaccuracy, so I'm going to try something a little different for this part, and see if I can improve things somewhat. So I took an old base plate and milled out a bunch of sacrificial fixture plates, and these can be bolted down to the base of the CNC and leveled in place. Parts are then super glued directly to this plate, and then the whole pallet is unbolted from the machine when the setup is done. The part and pallet are soaked in acetone until the glue dissolves away. So in my last video I spent a lot of time upgrading my CNC, and now I finally get to enjoy the fruits of my labor. So first, I'll start with the 3D touch probe, which is used to establish the X and Y origin, in this case the center of the bore. But it can also be used to establish the Z origin by probing up and down. And this brings us to the tool setter. The tool setter measures the tool offset, and frankly that's a whole discussion. But to keep things simple, I'm just going to explain my workflow. The machine measures the offset by touching the probe off on the tool setter. Now, every time a tool change command is issued, the machine will automatically move that new tool over to the tool setter and measure it. And in practice, this means that the Z origin remains the same, no matter how many tool changes I do. And this is a vast improvement to how I was measuring Z prior to this, which was with a piece of paper. So there isn't a ton to say about the actual machining of this part. The outline was roughed out, then the top was faced off. And finally, a contour pass finished off the part down to final dimension. And then it was time to bore and thread mill the M4 threaded holes that will secure the gearbox in place. And that's the first part ready to go. The next piece of the drivetrain equation is the output bearing, and this is the whole reason I wanted to do these parts over on the lathe in the first place. And that's because the bore on this plate will hold a very special bearing. So you probably know how a standard ball bearing works. You have spherical balls that ride around in a groove or race, and these are very good at supporting radial loads. That is, loads that run perpendicular to the axis of rotation. However, when it comes to axial loads, loads running parallel to the axis of rotation, well, the ball bearing kind of falls apart here. And do you know what kind of loads the elbow joint is going to be experiencing? The answer is all of the loads. Literally, all of the loads. So the hero we need in this situation is the cross roller bearing. And what exactly makes this bearing special? Well, the answer is in the name. This bearing has no balls. Instead, it uses rollers arranged in alternating pairs 90 degrees apart from each other. And these ride on V-shaped races that provide support in both the axial and radial directions. So this makes for a very strong and very accurate bearing that can also be made very low profile. And all of this is to say that roundness kinda matters when you're installing an expensive thin-walled bearing into a bore. So there's nothing like the lathe for making a bore truly round. But as I mentioned earlier, I've been struggling with boring. Basically, I find myself dialing in all my cuts, dialing in the DRO, taking test cuts to sneak up on the dimension, and I often nail those preliminary dimensions. So I dial in my final cut, and then completely overshoot the dimension. Every single time. And that's pretty much exactly what happened with this part too. I was going for a transition fit, and ended up with a pretty tight clearance fit. Loctite makes me the machinist I ain't. This part was finished up in the CNC, pretty much exactly like the first one. And good news, accuracy on these exterior dimensions has been outstanding. And that's another part ready to go. So now we need a way to connect the gearbox to the forearm. And if you're familiar with harmonic drives, you'll know that they actually integrate a cross-roller bearing into their output stage, and this makes it possible to directly drive many loads. However, this particular load is a bit more extreme than most. Basically, the forearm and wrist is cantilevered out quite a distance from the gearbox, and this means a significant amount of shear stress and bending moment are applied to the joint 4 connection. Think of it like this breaker bar. If I hold it out with just one hand at the very end and I move it up and down, well, it's very difficult to control and it lacks stability. But if I use 2 hands, even just part way up the shaft, well, now it's really easy to control and it's very stable. So we can accomplish the same thing in the robot by running a shaft between the gearbox and the output bearing we looked at earlier. And this shaft will rigidly connect to the rest of the forearm and hopefully provide all the stability and support we need. The shoulder on the shaft will prevent movement in the axial direction, and the support provided by both bearings will increase resistance to bending and will help distribute the load to the frame of the elbow. That's the theory anyway. So yeah, it's time to make a big shaft, and this is made a bit more complicated when we consider all the attachment points we need. So this means a 2-piece design. There's the shaft itself, which rides in the output bearing and mounts to the forearm, and then a flange that couples the shaft to the gearbox output. So I started with the shaft since it has a bore that locates with a mating boss on the flange. It's far easier for me to nail an external dimension like the boss, so I figure I'll have less of a chance of scrapping the part if I machine the bore first. And then I can machine the boss to custom fit it to the bore. As always when working on the lathe, I like to roughen the overall shape of the part, and then I let the part thoroughly cool before doing my finishing passes on all the critical features, because these parts get hot when you're removing this much material. And it was during this roughing stage when something magical happened. I broke chips in 6061 aluminum, and more importantly, I have actual proof. They said it couldn't be done, but they were wrong. Not to worry though, I was back to building birds' nests soon enough. I chose to orient the part with the bore side out, and this allowed me to machine all the critical features in one setup, which ensures maximum concentricity. So the shallow bore was finished first, and I used a telescoping bore gauge to get that as close as I could to dimension. So I started with the through bore. The further the tool sticks out, the more rigidity is lost. So I chose not to try to bore through the entire shaft from this setup. The through bore is just for cable routing purposes, and absolute concentricity doesn't really matter here. So I'll finish off the rest after I flip the part around. Next came the portion of the shaft that rides in the bearing, and this meant grooving out a channel and turning down the diameter to a shoulder. I can't test fit the bearing in this setup, so I'll need to rely on the micrometer to ensure I've hit the dimension. I'm really hoping for a press fit on that. After getting that down to dimension, it was time to flip the part around and dial it back in. And for this second setup, absolute concentricity is actually less important than making sure that the sides remain perpendicular to the face of the chuck. This setup mainly just consists of facing the part down to length and finishing out the through bore as close as possible to dimension. And I could finally test fit the bearing to double check that my dimensions were correct. And yeah, they were perfect. Nice. So it's time to move on to the flange. So I'm starting with the bore that interfaces with the gearbox, since there's a real possibility that I might blow that dimension and instantly scrap the part. So once again the part is faced, center drilled, and through drilled. And then I started the through bore for the cabling. And next it was time to bore out the shallow pocket that will locate the gearbox. And as I mentioned, this bore is pretty critical, and this is a pretty substantial chunk of aluminum, and I really don't want to scrap it. So I was very careful, and actually got the bore on dimension. So on dimension that I actually got the gearbox stuck to the flange. This caused some minor panic, but some gentle persuasion from the dead blow solved the issue. So the diameter was great, but the bore wasn't deep enough, so I carefully took a few more passes on the inside face. And one more test fit later, and the gearbox fit was perfect. And some gentle love taps once again convinced them to release their grip on each other. And here's a tip for inside chamfers. My tool is mounted a bit higher than the center line of the lathe, and the tool holder is rotated to somewhat approximate a 45-degree angle. And now I have the clearance to actually cut a nice chamfer. And this was followed by some finishing passes on the outside dimension. And that's all of the critical features in this setup. But before I flip the part around, I can make the next step a bit easier by machining a groove to act as a reference for when I dial it back in. And it's time to do that now. So I dialed the part back in concentric, and then I position the indicator so that it reads against the inside of the shoulder. And this lets me check the parallelism of the part. You then basically have to alternate back and forth between the two positions, dialing the part in concentric, and then tapping the part in to get it parallel. And you can spend as long as you want chasing perfection, until you just completely give up and just take the damn cut already. So now I could start turning down the boss feature. And then start taking the flange down to length. And once this was close, I did a bunch of measuring and test fits until I had a nice fit with the shaft. And that pretty much covers the lathe portion of these parts. But they aren't nearly done at this point. Now they need all those pesky mounting provisions. And these mostly consist of some pretty deep, narrow aspect bores. And bores like these are very difficult to do on a CNC. So I need to use a manual mill to machine up these features, which first meant finding a way to fixture these parts. So I strapped the forejaw down to the table and then clamped up the flange. I am now eating a lot into my already heavily limited Z travel, but I think it should be just enough. So now it was time to dial in the center of the part. And doing it this way with the dial test indicator feels pretty old-fashioned. Once the origin was established, I programmed the hole circles on the DRO, and then it was just a matter of chasing coordinates as I cycled through the various tooling. So all the holes were spot drilled, and then the through holes were drilled. And I used an end mill to plunge out counter bores for the bolts. They do make special tools for this, but an end mill works fine in a pinch. Finally, I drilled out the tapping drill size and used a tap and follower to thread up all the mounting holes. And these holes allow the two parts of the shaft to bolt together. And now we hop back over to the main body of the shaft, and basically we have a bunch of threaded holes that are used to attach the shaft to the forearm. And then we need a bunch of through holes to accommodate the bolts that attach the two halves together. And once again, I used an end mill to plunge out the counter bores for all those mounting holes. And finally, I tapped out all the threaded holes with the tap and spring-loaded follower. and it's time to look at the final piece of the Axis 4 drivetrain, and that's the motor mounting plate. And this is a fairly large plate that not only acts as a large piece of the frame, but also mounts and aligns the motor with the gearbox. Now, a good portion of the pocketing on this plate is just for weight reduction, so those dimensions aren't critical. Which is probably a good thing, because inside dimensions still tend to come out a bit undersized. So I usually need to compensate for that in the CAM software, and honestly, I'm not sure why that's the case. But once again, we do need to get the outside dimensions correct. But luckily at this point, the CNC is doing a pretty good job consistently nailing outside dimensions. The motor will get mounted on a plate that rides in this pocket, and a screw jack serves to tension the belt that connects between the motor and gearbox pulleys. So I don't want to keep harping on about the tool changer, but I do just want to point out that I'm now routinely doing anywhere from 6 to 10 tool changes in a setup at this point, and I've begun to experiment with using different tools for different types of operations. For example, I've been using an O-Flute for all of my roughing, and now I'm experimenting with using 3 flute end mills for my wall finishing passes. And 2 flute end mills seem to be giving nicer floor finishes. And you know, I've realized something kind of vital during all this. I don't know shit about machining. I still have a lot of experience to be gained through the school of hard knocks. But at least now I feel a lot more free to start experimenting, since I've reduced the pain point that is tool changes. So really, investing in a tool setter is ever so slowly helping me to become a better machinist. Hey, whatever justifies the tool budget, right? So at this point, we're cranking through this assembly. But before we move on to something more challenging, we do need to machine up a few more frame parts. These cross plates are just basic frame components, and really just the exterior dimensions matter. And at this point, these parts are practically child's play. Some mounting holes were bored and thread milled, and a bunch of weight-saving pockets were roughed in with the O-Flute. And finally, all the finishing passes and a chamfer pass wrapped everything up. And yeah, I had to make 2 of these parts. So all of these parts obviously take a lot of time to produce, and between this and my day job, it's a little tough to find time for my own personal learning. And that's where Brilliant is frankly brilliant. Brilliant helps you get smarter every day, with thousands of interactive lessons in math, science, programming, data analysis, and AI. With Brilliant, I can learn a little bit every day, and it only takes a few minutes of my time. And with the Brilliant app on my phone, it's easy to sneak in a lesson or two while I'm waiting for a part to finish up, for example. And honestly, Brilliant's courses are super interesting and interactive, and I often find myself making an excuse to sneak in a quick lesson, no matter how busy I get. And what's amazing is how even just a little bit of time spent on Brilliant every day actually adds up to some pretty major results over time. If you're into robotics, you're gonna have to know some programming, and this is admittedly a pretty big weak point for me. So I've been really enjoying Brilliant's programming courses, like Thinking in Code or Programming in Python. And let's be real, if I'm learning something from them, you definitely can too. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/cinemamechanics or scan the QR code on screen, or you can click on the link in the description. You'll get 20% off an annual premium subscription. Thanks again, Brilliant, for sponsoring, and back to it. So we're 5 plates in, and all of these plates slide into pockets on the 2 side plates that form the largest part of the frame. And usually the common wisdom when machining up fits like this is to machine the pocket first, and then machine up the external dimensions to match those pockets. And if you remember, this is exactly how I did the bore and boss fit on the shaft. And usually this is because it's harder to cut and measure inside features as opposed to outside features. But things are a little different when you're dealing with something as repeatable as the CNC. Gradually sizing up an internal feature on the CNC is as easy as adjusting a few cut parameters in CAM. And this becomes especially useful when using superglue to fixture your parts, as it becomes pretty hard to do any test fitting as you go. And we're going to custom size each of the pockets to ensure we have a good fit with the existing parts. So when we look at how the elbow integrates into the rest of the arm, we face the same question as before. Do we cantilever the load and just support the entire thing from the gearbox? And a lot of robots are designed in this exact way. The other option is to support the elbow on both sides by putting a bearing opposite the gearbox. And I chose this option for a few reasons. First off, it just seems more stable. The support bearing provides an extra constraint that makes the load on the gearbox output a lot more predictable. Secondly, it allows me to distribute the load from the elbow to the bicep over two thinner plates, rather than having to rely on one super beefy plate to support the entire load. And this is a lot easier for me to manufacture. So I'm going to start with the bearing side first, for reasons I'll get to in a little bit. And since this part is so complicated, it really pays to take the time to think through the order of operations. So first decision is which side to work on first, and this is made pretty obvious since I plan to fixture with superglue. So if I machine away all those pockets first, there won't be much surface area for the glue to hold everything securely and set up to. So best bet is to machine the outside of the plate first, which leaves a nice flat surface for gluing down later. Besides facing, the only feature that absolutely must be machined in this setup is the bore that locates the support bearing. But there are some other benefits to be gained by doing a few more operations in this setup, so I'll explain as I go. So first off, the outline of the part gets roughed out. The benefit of machining this outer profile is that the part now has a reference edge that can be used to aid in alignment in the next setup. Next, the bores were roughed in, and the whole part was decked off to final height. And then finishing passes were run on the outside profile to bring that to dimension, followed by the same procedure on the through bore. And I slowly worked my way up on the bearing pocket, gradually removing material until I achieved a good fit with the bearing. And my suggestion here is to always do a spring pass or two before adjusting your tool path. There always seems to be a bit of extra material to remove in every spring pass. Now this bearing is also a fancy cross roller bearing. However, this one doesn't really require an absolutely perfect circle to ride in, and this is because we're really just end mounting the bearing, and the pocket is just being used to ensure alignment. But the bearing isn't actually running in this surface, so we can get away with doing this on the CNC. So we might as well go ahead and bore those mounting holes now. And we might as well finish up all the other bores, the through holes for the bolt connections to all the various cross plates. And finally, some threaded holes that will allow us to mount a side cover later. And the benefit of doing all these bores now is that it saves some manual labor later, since I can now chamfer all these holes and every other accessible edge in this setup. And that wraps up all the machining for the first side, and the pallets were removed and soaked in acetone. And here I learned an important lesson about notching the pallets. I had faced off one of these pallets and pretty much completely removed the grooves, and this meant this part was locked down. And even after a 24-hour bath, the plate would not move, and it failed to budge after some good wax from the dead blow. Propane torch got it though. But yeah, super glue is plenty strong. So now I can reinstall the pallets and level them once again, and this time I machine a reference edge into the pallets, which gives me a way to align the part. So the part was flipped and glued into place against the reference edge. And next I used the 3D touch probe to center up on the through bore, which is the origin for setup 2. So first op was to face the part to final depth, and then it was time for bulk material removal, in the form of adaptive roughing with the O-Flute. All the locating pockets get roughed in, along with a whole bunch of additional pockets for weight reduction. And this took a long time on my little router. And next I ran finishing passes on all the floor surfaces with the 2-flute. And then followed up with the 3-flute, finishing the outline of the part and the weight-saving pockets. Then it was time to finish the locating pockets for all of the cross plates, and these were done one at a time, and each part was test fit before moving on. An off-camera chamfer pass followed, and this first side plate is all done. So now we have another side plate to work on, and this one is a bit trickier than the first, and this is because of this shallow bore that locates the Axis 3 gearbox. I've already mentioned that it's difficult to measure shallow bores with a telescoping bore gauge, and this tends to get worse as the bore gets larger. And this bore is pretty large at 170 millimeters, or approximately 6.7 inches. Anyway, I don't have a bore gauge big enough to cover 170 millimeters, nor do I have a micrometer large enough to measure it. I don't have gauge blocks and I don't have gauge pins, but what I do have is a pretty big digital caliper. but measuring inside dimensions with a caliper is an educated guess at best. Normally in cases like this, I'll do a test fit with the actual part, but I don't have the depth in this situation to make that work. So a half-baked plan was starting to form. But first I have to confess the biggest screw-up I've made on this project to date. So I bought all 6 of the harmonic drives for this robot quite a while ago. When you're designing around components, and you're buying those components used, you just kinda have to snatch them up as you go, since it would be pretty bad news if those components weren't actually available when you need them. So in the months while I was hunting for these gearboxes, I was using the manufacturer-provided CAD models as my reference for all the designing. So without getting into it too much, let's just say that in the real world, components can vary a little bit from the CAD model, and sometimes you just purchase the wrong component altogether, without realizing it until it's way too late. eBay came to the rescue once again, but this time there's a price. In a stroke of fortune, the exact model I need is available, and the dimensions they list align with the manufacturer's specs. But it is by far the most expensive gearbox I've had to purchase for this project. And that's on top of the gearbox I've already purchased. You know, the one that's completely useless to me at this moment. Oh, whoops. I clicked on my Patreon page, where you can get early access to videos and other great perks. So weird. Don't know what happened there. So the new gearbox came in record time from Korea, and yes, it's the right model this time. So now we can finally get back to my half-baked plan for machining up the bore, and the idea is to first create a go, no-go gauge. So basically I'll turn down a plate in the lathe to be the same diameter as the gearbox flange, and then I can use that to test fit as I machine up the part. So how am I going to measure up the diameter if I don't have a large enough micrometer? Well, I'm going to use the calipers. But instead of relying on the numbers, which may or may not be accurate, I'm going to do it more by feel. So I measured the flange diameter of the gearbox, and then I locked the calipers while ever so slightly squeezing them together. I then took note of how tight the calipers felt as I moved them over the diameter. And after roughing the plate in on the lathe, I used sandpaper to fine-tune the diameter, and I used the same pair of lock calipers to check the feel of the gauge plate. And once these all felt the same, I decided the gauge was probably good to go. And is this all a terrible idea? I don't know, maybe. I don't know shit about machining, but we're gonna find out. Unlike the bearing side, all the important locating features for this plate are on the inside. So in an effort to simplify, I decided to limit setup 1 to a facing pass only, which meant not having to deal with a reference edge or probing or anything when it came time for setup 2. And this all was machined up in pretty much the exact same way as the other side plate, except there was even more material to remove. And once again, I ran a finishing pass on all the non-critical surfaces first, and then ran individual finishing passes on all the critical pockets, and test fit each of the plates one at a time to ensure a proper fit. You know the deal. And then came time to finish off the large shallow bore, and I ran a bunch of passes and spring passes until the fit of my go, no-go gauge was just right. And fingers crossed that that actually means something when it comes time to install the actual gearbox. So then came a bunch of threaded holes for the gearbox mounting, as well as all the through holes. And that should be the part ready to go. But something was bothering me. I wasn't going to have nice matching chamfers on both sides of the part. It really bothers me. So I machined in a straight edge and prepared for setup 3. Because I really can't help myself. But you know what, they look great, so minimal regrets. And after all that, how'd the gearbox fit work out? Absolutely perfectly. It's the exact transition fit I was going for. Luck? Skill? I'll let you be the judge. I just have a few final parts to tie it all together. And that's the top and bottom caps that finish off the box frame. And it's amazing how parts like these, which would have been whole projects in and of themselves just a short while ago, now almost feel a little routine. So maybe I am learning something about machining. Enough to be dangerous anyway. But dangerous or not, this assembly consisted of no less than 11 separate parts, and somehow miraculously, they all fit together. Like a glove. It's pretty satisfying to see a little bit of payoff from a lot of hard work. And this stage of the project went almost a little too smoothly. Almost like a dream. Click.